Atoms don't always like to be alone, sometimes they are, but mostly they like company, but only with a few of them, the right number that complete them like a puzzle. What is the right number? Well, it can vary a lot, but guess what? It's determined by our little sad friend, the electron. For some reason, as chemistry why, an atom is really happy and relaxed when there are 8 of them around it. Or you didn't ask the pronouns, my fault. Please note that we are talking about electrons in the valence shell. This is also the reason why scientists take so much time to find out about the existence of the noble gases, because they always have 8 electrons around, and so they can never react at all with other atoms, which is mostly why we found out about the existence of elements in the periodic table throughout history. Anyway, how do all the other elements manage to get 8 valence electrons around them? Easy. Sharing or stealing. Either way, by creating what is called a chemical bond. Now, chemical bond came in different flavors, but we mostly make 2 differences: intramolecular bonds, how atoms form molecules, and intermolecular bonds, how molecules stay together. Let's start with how the molecules are formed in the first place. 3 types of bonding can take place depending on which atoms are interacting: the covalent bond, the ionic bond, and the metallic bond. The covalent bond is your standard, happy and strong kind of bonds. It involves 2 non-metallic atoms that simply share their electrons in ways that allow both of them to reach a total of 8. Sometimes though, one of the 2 atoms is bigger than the other and, as a consequence, attracts the electrons in its direction, causing the molecule to have a positive polarity and a negative one. A perfect example of this is the water molecule, where the oxygen is bigger than the 2 hydrogens. This is also why we call molecules with a covalent polar bond hydrophilic. Now, what happens if one of the 2 molecules is way bigger than the other? This is the stealing part I was talking about. The big atom rips the electron away from the little one. The resultant particles are 2 ions: a cation, a particle with a positive charge, and an anion, a particle with a negative charge, which stay together to keep the electric charges balanced. This is basically an atomic scale Stochondra syndrome, where the victims of the theft simply can stay away from the thief. Yes, I do know Stochondra syndrome is supposed to be with kidnappers, but you get it. When the ions are together, they make something called salt, a structure that has nearly the same force of a covalent bond, but when the salt is put into water, the polar region of the water molecules rip the ions apart from each other. Now, remember when before I said that covalent bonds occur only with metallic atoms? That's because metallic atoms prefer something called, and I hope you're seated for this one, metallic bond. Yeah, fantasy, right? In this kind of bond, all of the atoms of a certain element are together in the form of positive ions, which have, all around them, what we call a sea of electrons that keep them in place. Note that both the ionic bond and the metallic bond form a reticulum of atoms kept together by the electrostatic force, and not exactly a single molecule. Now, moving on with the intermolecular bonds, we have the dipole van der Waals forces, the hydrogen bond, and the hydrophobic interactions. They can all manifest between 2 or more different molecules. The dipole van der Waals forces are a family of chemical interactions based on the electric charge or the polarity of a certain molecule. This polarity can attract the opposite pole of a near molecule, but they are all very weak bonds. The hydrogen bond occurs when a hydrogen atom has a covalent bond with an atom with a big electric attraction like oxygen, nitrogen or sulfur, and is also near another atom with a big electric attraction. This is the chemical bond typical of the water, which is a molecule capable of an astonishing number of hydrogen bonds, 4 with other water molecules. This is also why ice is less dense than liquid water. The water molecules in ice are kept at a certain distance thanks to the hydrogen bonds, while at a higher temperature the molecules are capable of slide over each other and so can't really form the bonds. Last but not least, we have the hydrophobic interactions. Remember when before I said that molecules that present a polar region are called hydrophilic? Well, all the other molecules are called hydrophobic because they don't have any polar region and so can't bond in the same way that hydrophilic molecules do, and this causes a natural repulsion between polar and non-polar molecules. It's not like oil in water, it's literally oil a non-polar molecules and water a polar molecule. That said, I honestly hope I covered all of the chemical stuff because, in my opinion, it's kinda boring. Now that you know what are all the little things that make the universe and you have a general idea of how they behave, we can move on and start talking about how all of these dead things combine to make you, a flower, a bacteria, and that thought thing you asked about a while ago, the biomolecules.